Can I get your password? Thank you, everyone, for coming. I'm excited to tell you today about a new area in the field of robotics, which is known as soft robots. And what I'm going to try to communicate in the talk today is about what soft robots are, give some examples of research on these soft robots from my laboratory, and as the title says, why they're for humanity, how they can help with our safety, our health, and our quality of life. So first of all, let me just do a little bit of an introduction to what soft robots are. This shows a kind of spectrum from mostly stiff robots that have a few compliant elements. The one on the left, possibly you've seen before, that comes from a Stanford professor in my department, Mark Kokoski, who was one of the first to recognize that robots could take inspiration from animal biology and use some flexibility in their joints to improve their natural dynamics. And so he made robots that can run fast like cockroaches. Whether or not that sounds good to you may depend on how you feel about cockroaches, but nonetheless, it created some of the fastest small robots in the world that could be used for surveillance and checking out unknown areas. All the way to the other end of the spectrum to something that was just published last year called the Octobot, which is entirely soft. So everything in it is soft, even the circuitry of it is soft, and its chemical reactions and fluids within the body of this soft robot that even controlling cause it to move. I think the challenge of some of these very, very soft robots is they're sort of cool from a scientific perspective, but all this Octobot really does is kind of move a little bit. It doesn't really do anything in the environment, and we don't really have a way for it to help people. And so along this spectrum of soft robots, I'm going to be showing you some examples of several projects from my lab which have varying levels of softness, but are all designed to solve real-world problems and affect humanity. And so these examples are as follows. The first one is going to be a hands-on simulator originally designed for medical simulation, but could also be used in other applications. And here it's about haptics. Haptics means the sense of touch, and we're trying to build devices that feel like real-world objects, even though they're artificial. And the second project is flexible medical robots that are designed to be just right to go through the body of a specific patient to be as minimally invasive as possible. And then the last one is about some new soft robots. These are very recent, just published for the first time this summer, about robots that effectively grow out of their tip and can grow like vines or plants and have some really interesting properties and potential applications. And I'll also try to highlight for each of these some of the awesome students that have contributed to these projects. So first of all, I'm going to talk about this hands-on haptic simulation. And the reason why we would like haptic simulation in medicine is so that if someone is training to be a doctor, they can practice not on you, the patient, initially, but they can practice in some kind of virtual world. Now, there exist on the right-hand side these virtual environments that you can kind of poke at through a stick and get force feedback, and those can be very realistic, but the interaction is limited to poking at something with a stick. On the other hand, you have on the left side these mannequins, which you can really get this hands-on training if you want to learn how to palpate or do certain kinds of procedures. It's very natural, but these mannequins are static. We can't change the way that they feel for different pathologies, and so we are missing something in between these two, and we'd like to have the best of both worlds. Another thing to consider when we're thinking about designing these haptic or touch feedback devices is that our sense of touch is really complicated. One way to simplify it or to think about it is two major categories, is to say that we have force feedback devices. These are devices that push on your arms or your hands, and you feel large-scale motions or forces in your body, and typically these are done by poking through a stick. On the other hand, there's cutaneous or tactile devices which stimulate the skin. And this is often achieved through an array of little pins or other tiny motors or actuators that can provide distributed information on the skin. And it's this combination of what you feel in your skin and what you feel in your muscles and tendons and your joints that all together give our perception of the world around us and also of our own bodies. And so ideally, you'd like the best of both worlds here. You'd like to have these immersive, realistic medical simulations. And while there are many haptic devices that have been designed, there's this new concept of something called active surfaces. This is surfaces that can change their shape and mechanical properties, and we wanted to try to do this for medical simulation. So the idea is not to build an entire mannequin out of this stuff, because that's a lot of motors and it's very expensive, but that you have a little block of material that can change its shape and mechanical properties, but the user, the trainee, would see a visual display of a patient, like the one shown at right. And their hand is being used to palpate and look, for example, for a hard lump in soft tissue that might indicate cancer. And in this case, the user can reach out the hand, the robot can move the block underneath the hand, and then the device can reconfigure itself to feel a certain way. And then if you want to touch a different part of the patient, it could move over there and reconfigure itself so it feels appropriately. So that's the dream for how this all works together. I'm going to focus mostly on just the reconfigurable device itself and how this works. So this is an example of one of the very first devices that we built. It's a little 4-cell array, and each cell can change both its shape and mechanical properties. In this case, we're trying to simulate what the surface of organs or the surface of the skin feels, so it's basically kind of a soft, lumpy environment, which matches well to the soft robotic technology that we have. And the way that it works is actually pretty simple. The way that it balloons up is by air pressure being applied from below. We can also pin certain nodes in between these cells, and that can help pull it down and help us control shape. But the real sort of secret in this device is that to make things hard or soft, we have these silicone chambers that are filled with coffee grounds. So why coffee grounds? So if you've been shopping at the grocery store and you buy vacuum-packed coffee grounds, you know that the package is really hard and stiff. But if you open up the bag and mix your finger around in it, of course, it's very soft and movable. So the vacuum is actually kind of locking the coffee grounds together and changing it from very soft to very stiff. So by vacuuming the air out of the chambers in the device, we can actually make it hard or soft. And there are many other smart materials that could be used, but coffee grounds were readily available in our research lab, and the graduate students found that to actually be very effective material for doing this kind of jamming behavior. So in order to figure out, once we knew that this approach would work, we wanted to say, can we have a simulator that would allow us to figure out how many cells we would need to create certain types of display? So we're able to say, if we have different shapes of cells and different combinations of them, can we come up with algorithms to create the shapes that we want, and we can test this all in a virtual environment before we build the devices. And that's important because building the devices is actually a huge pain. And this picture I show not to be proud of what a mess it is to actually build a large device with lots of cells in it, but to actually show that this is one of the main challenges of soft robotics right now, in that if you want to have a bunch of chambers, each of which can be changing its mechanical properties and changing its shape, we need to be able to get beyond this kind of curse of dimensionality of all the different pneumatic lines and cables and actuators that are present. So I always promise my PhD student I would show the slides so everybody knows how hard he worked to build this system. And in the end, although it is a mess to build, you can actually have a very effective system in the end. So the way, this might be playing sound, turn it off. So this is a 100-cell array, which the guts of it were shown in the previous slide. And every one of the cells has these properties that I discussed earlier, where you can change the shape and the mechanical properties. And in this case, for some reason, the conference we were submitting to wanted videos that all share the property of having a rubber ducky in it. So that is why it's going in the shape of a rubber duck. And there could have been any shape. But the idea is that we measure it with one of these 3D Connect cameras that you can get with your Microsoft PlayStation. We use that visual information and depth information for feedback, and then we control the device to be in that shape. And simultaneously, we can control it to be hard or soft in different locations. Ultimately, though, for creating any general shape, this is somewhat disappointing. We could actually do a pretty good job of recreating the abdomen and lumps and bumps in that area, But now if you want to think bigger about creating any shape, any mechanical property, this kind of 2.5D, that is an XY plane that can go up and down, this kind of array of cells, isn't necessarily the optimal way to go. And you can see it doesn't really create a duck very faithfully, since duck is really 3D and not a 2.5D object. So the thing that we're working on now as we push forward with this project is really thinking about 3D shapes. So this is actually a heart model here, and the idea is that we can simulate hearts with different pathologies, an enlarged heart, a heart with muscle weakness, and so it has softness in certain areas. And then rather than trying to arbitrarily have some set array of cells that would require all of the complexity that I showed earlier, instead we can simplify this by saying we're going to have an algorithm where there's a few specific target shapes that we want to hit, and we want to design the optimal device to start with that can be morphed into those different target shapes and not any arbitrary shape. And that actually really simplifies the design, makes it more elegant, and actually makes it something that could be a commercial product. So this is something we actually collaborated with on a company to work on medical simulation. But I think this concept of objects that change their shape and mechanical property have a lot of other interesting applications. These include interesting human-computer interaction scenarios. So one example might be in consumer products. So let's say you wanted to buy a sneaker, and you wanted to get an idea of what its shape and size were other than just seeing it on a screen on your computer, or even in a VR environment where you're limited to visual interaction. So if you had such a device on your desktop, it could pop into the shape of that shoe. And then you might say, well, I don't like the shape of the toe box. I want to push it down, and I want to change its shape a bit. Well, that manipulation could then be recorded, sent back to the computer, even be sent back to the manufacturer, who then might be able to create for you an ideal custom shoe that matches the way that you shaped it. So there are a lot of different concepts here for how this could be used, but the idea of a changeable project or digital clay, I think, is one of the dreams of engineering in general. And thinking of this from a perspective of, what are the techniques and algorithms that you could use to make these changeable objects are going to start to get us there. At the moment, mechanically, practically, we can do this at the macro scale. But with new developments in MEMS and new actuation technologies and smart actuators in particular, there is the possibility to make something that's more like a truly changeable product a reality in the future. So that is one kind of soft robot, and it's a haptic or touch feedback device. I want to tell you now about a very different type of soft robot. It's not soft in the sort of stretchable sense of the silicone rubber that was used in the previous part, but it's soft in that it's flexible, and it's designed to go inside the human body. And the idea here is that you would like to get deep inside a patient's body in the most minimally invasive way possible. Now, robot-assisted surgery is not science fiction. Many of you probably know that there are commercial surgical robots. Hundreds of thousands of procedures are done every year. Prostate surgery is actually the biggest application right now for surgical robots because it allows clinicians to do the procedure in a minimally invasive fashion while causing less damage to the body. And these surgical robots have actually had a lot of benefit, but they also have a lot of cost. And then there are patient populations that the robot cannot be used with. Small children, the tools are a little bit too large. And then there are sometimes obese patients or people with other shapes of bodies that they just can't find the right path for these straight line tools to get inside the body where we want to go. And by the way, I'll promise you that there are no gory pictures in this, in this talk. I have my gory picture talk, but I decided to leave it out for the alumni event. So our idea here is that it's not about just designing the big robot that can really precisely move the tool to a particular location, but rather thinking about it from a patient-centered perspective. So what we want to do is have a patient-specific design workflow where you have images of the patient, for example, from a CT scan. You build a 3D model of the inside of that patient. And then there's a surgeon design process. The surgeon could actually design the shape of the robot they want that would snake through the patient's body in the most minimally invasive way possible to reach the target without puncturing through other organs. Right? And then once the surgeon designs the robot that they want, they don't have to pick the motors or the bearings or the material, but they design the shape. And then we can fabricate it now using newer 3D printing technology that allows us to fabricate softer materials. And then we can actually drive it, attach it to a robot external to the body, and then drive this snake-like robot along the path that the surgeon designed it for. So there are many types of robots that could be used in surgery, and the specific type of robot that lends itself really well to this design methodology is called a concentric tube robot. And this was something developed quite a while ago, almost 10 years ago now, by a student of mine. And the way that it works is it uses a series of tubes, each tube being highly flexible. In this case, they're made out of nitinol, which is a super elastic material. And you put one tube inside the other, and you can put a third tube or a fourth tube or a fifth tube if you want. And you pre-curve those tubes. And so as they insert and spin with respect to each other, you can get this tentacle or snake-like behavior. And what that allows you to do is have a very thin kind of backbone to the robot and have all the motors and the parts that drive those tubes in and out and spin them, keep those big motors outside the body. And that lets us have a really tiny instrument, which is very appropriate, for example, for the pediatric urologist here at Stanford that approached us about designing a new robot that got around the limitations of existing clinical robots. So this is not our doctor collaborator, but my graduate student, Tanya, using the 3D virtual reality environment where she's kind of immersed inside the patient's body, and she's designing the tubes. In fact, in this video, it's showing her designing the desired tubes outside the patient's body, and that's just because all of you really wouldn't be able to see what she was doing if she was really inside the virtual patient, because you'd be surrounded by all of these organs and such. So just for visualization purposes, for you, she's designing it outside the body. And then once she designs the robot, she can simulate it, and she can say, okay, is the robot actually going to behave when it goes into the body in the way that I designed it for? And again, normally she would do this inside the virtual patient, so she could be testing it with respect to that patient's actual anatomy. And then we print it. So I kind of made it sound like this hot new 3D printing technology is what's enabling this, and it is, but it's not like this is the most expensive, fancy 3D printer. We're doing this on a MakerBot. So those of you who have ever used a 3D printer have probably heard of MakerBots. They're on the cheaper end. They're about $3,000 for the highest end MakerBot. And one of the standard materials that they have is called PCL, and it's a biodegradable polyester, and this kind of material is actually already used in medical devices and even in sutures. So it turns out that making these robots out of PCL and printing it on a very standard, cheap 3D printer is totally feasible and even relevant to actual clinical practice. So once you have your tubes, you print out the ones that the surgeon designed, and then you have to attach them to some motors that can insert and spin each tube in order to create this tentacle-like behavior. And this as well doesn't have to use 3D printing, but we wanted to make this actuation system as small and lightweight and easy to move around the operating room as possible. So once again, we took advantage of 3D printing to make a really unique transmission system. We like to call it a waffle gear, where we really minimize the size and shape of the transmission by having these sort of gears go over these waffle patterns in order to get the most degrees of freedom in the smallest amount of space. And this whole thing is made of plastic, so it can be very lightweight and handheld and cheap. And there's a couple pictures on the right showing different ways in which it can be held by a person or even held by another robot or a passive arm in order to be used in a medical procedure. So we put all of this together, all of these components of the actuation system, and we are looking for NIH funding in order to finish doing animal studies with this. But in the meantime, we have done this in an artificial patient. We took the same model from the CT scans we used to design the robot to then 3D print a patient and their artificial tissues to represent them. And so we took that model, made an artificial patient, and then these clinical robots are currently not autonomous. Although I live in Mountain View, there are self-driving cars all over my neighborhood. We are not ready for self-driving surgical robots because although the self-driving car problem is very, very difficult, there are rules of the road, vision is not as occluded as it is inside the body. The inside of the body is very messy. There's manipulation of tissues, and the response is not well understood. So the human has to be in the loop to drive this robot. It's not operating by itself. So the same surgeon who designed the robot has an idea not only of the shape they wanted to follow, but how it should move along that path. And so that same surgeon can then use this master robot, which actually is a haptic device, in order to command the positions and orientations of the robot inside the body. So kind of full circle, the same surgeon that designed the robot can then teleoperate it in order to control its movement inside the patient. And we've demonstrated this, showing that in our artificial patient, we can go around ribs, we can go in at angles that would be less invasive to a patient. For example, this represents an 8-year-old with a kidney stone, and with 8-year-olds, the size of their body is such that there's no straight line path to get to the kidney stone with a needle. And so instead we curve around the ribs, avoid the lungs in order to get to that target. And we've shown that we can do that in these artificial tissues. So again, it's a soft robot, and the softness, that is the flexibility of the plastic in these tubes, enables it to have the kind of movement capabilities that it does, but it's a very different kind of softness from the first case, where we're not really changing its stiffness, and we're not really fully changing its shape by blowing it up, but rather the interaction of the tissue of the tubes causes different types of bending to change the shape. The third project is kind of a mix of those two previous soft robots. It's like the first one in that it uses pneumatics, it uses air pressure to run, but it's also like the second project in that it makes a long, skinny tool, and it might have applications in medicine. And this project we like to think of as a robot growth that's biologically inspired. And the idea is that there are many things in nature which grow, ranging from very small things like pollen tubes to vines, which if you're a gardener may be the bane of your existence. But for us, vines are really cool because they can climb along walls, they can get through small crevices, and they're able to do that because unlike animals, which have to move their whole body, they just extend from the tip, and that tip can actually be quite tiny. So the way that we achieve this growth, it's not magical. We're not magically creating material at the tip. But what we are doing is we're feeding more plastic through the center of a plastic tubing. And if you're having trouble picturing mechanically how this works, if you've ever seen one of those water snake toys, they're kind of like a torus that is elongated and they flip in and out of each other. My kids have them. They love them. Fun toys. But now instead of thinking of it as constantly rotating about itself, we just keep feeding more material through the center, and that allows it to grow, as shown in there. Now, what this allows is extremely large change in length. So unlike a classic snake robot where the whole snake has to move its body, we just keep growing like a plant does. And so, let me see if I can get these videos to play. So the video on the top right shows one just growing vertically against gravity until eventually it buckles and falls over. The ones on the bottom show a whole roll of this tubing that keeps getting fed out. And the right bottom video shows the end result from having just pressurized and fed this tube through. And this is just a couple PSI. I think we grew this about 70 meters. Our goal had been to grow at the length of the Stanford football field, and we pretty much got there. We only ran out of plastic. That was, I think, our limited issue. Although it turns out you can get really big balls of these plastic, really big tubes of them from Amazon. So we now have a good plastic supply, and we'll never be troubled by that again. And so the cool thing is that we can grow at very, very long distances. But you might say that this is not a robot yet. It might be soft, but it's not a robot. It becomes a robot when we can actively control it. We can tell it to turn left and turn right. And so to do that, we need to have a way that it's not like putting motors and joints like with a classic robot. We have to find a way that at the tip it can change its mind about which direction to go. And there are two ways to think about doing that. One is a way that's permanent. And in the permanent method, we have pinches on the plastic. When you pinch the plastic on one side, it curves towards the pinch. And if we let that pinch peel off, we let it unpinch, then it will go straight. So we can have this permanent direction change just by letting pinches unpinch when we want it to go straight. On the right-hand side is something that's a little more complicated, but more flexible, and that is reversible direction change, where we have multiple kind of pneumatic tendons, one of which is shown in the video on the right now, and then we put those around the outside of the backbone of the growing robot, and those can be controlled in a reversible fashion. You can look left, you can look right, and then you can decide where to grow. And we've done this with overhead cameras, as well as, on the right, having a camera that stays mounted at the tip of the growing robot. And that way you can always look at where you're going. And although in some applications like medical, there might be other applications where having an autonomous robot's useful. So we've shown that based on the camera images, we can autonomously grow to targets. And those are non-reversible methods in that video. This set of video is the same thing, but with the reversible methods. We're growing towards a light using a camera mounted on the tip. And you can start to imagine now the applications where this would be useful. So I'll give you some examples of these applications. This is like our robot gym showing all of the different actuation technologies, some of them just growing, some turning, and it being able to do several interesting tasks. So the top left, it's popping through a very small hole, much smaller than its own body diameter. The middle one shows the robot going through a kind of obstacle course of going through a bath of glue and then getting punctured by some nails, and it just keeps going as it feeds more material through. On the right, along the top, is a firefighting robot, which actually grows over the fire, and then the fire melts the plastic, and then the water inside the robot puts the fire out. Cute, huh? We like that one. And then the bottom one is actually really exciting because it starts to show some very simple manipulation capabilities of such a robot. So here we grew it under a door. We pre-mechanically programmed it through this non-reversible direction change to grow up and around and hook around a lever which it could turn, for example, to turn off a gas leak or something like that. So you can imagine a search and rescue or disaster scenario. You could get into places where people don't want to go and then do some kind of manipulation task. So this is a very new kind of soft robot, and it's just taking advantage of the flexibility of that plastic material and the pneumatic pressure to achieve these interesting behaviors. So I hope that gives you a good introduction to the kinds of things that we can do with soft robots, which are very different from the traditional industrial robots or even medical robots that exist on the market today. And although there is very few things happening commercially right now with soft robotics, I think over the next decade, you'll start to see an explosion of products and new research in this interesting area. And I'll end by thanking you for listening and all of my awesome students that contributed to this work. Thanks. And I get the nod from Indrani. I have time for a few questions. Yeah?
Super interesting. Congrats.
Thanks.
Can you talk a little bit about some of the technical challenges that you're facing now that, that are preventing you from basically turning this to kind of commercial applications?
Yeah.
What are the kind of things that you're
well,
sorting through?
I think two big technical challenges. One is modeling. The understanding and predicting how these soft robots will behave, especially when they're interacting with the environment, is complex. And especially when you have stretching and bending and that the materials are purposely uncertain. Sometimes you want that uncertainty because it can conform to the environment, but it can be difficult to predict what will happen. So that makes it difficult to, say, optimize a design. Another issue I would say is sensing, especially in stretchable surfaces. So the first example, the medical simulation device, I mentioned we use a Kinect camera from the overhead to look at the shape. But that's not really a good approach because as soon as someone puts their hand out to touch it, we've occluded the thing that we're trying to sense. So we would like embedded, stretchable, flexible sensing in all of these objects. And while there are such sensors that exist, the wiring problem of how do you get information from all of those sensors so that you can reconstruct the shape is still unknown. Yeah, thanks for your question. Yeah?
On the tube one, there's a camera at the tip, because the tip keeps changing as the material unfolds, so how do you mount a camera there, or how are you doing that?
Yeah, great question. So there are several ways to do it, but we think one of the most effective ways is if you put a camera at the tip and then you tension a string from the platform the camera's sitting on through the center of the robot. When you pressurize and the robot grows and more material comes out the front, it just pushes the camera forward. And as long as you provide enough tension on that string so that the camera doesn't fall off, you want to keep it against gravity or any other forces, you need to keep it at the tip. If you just apply a little bit of tension, then the camera will get carried with it. Yeah. Maybe one more question? Yeah.
You said that you could put the pinches in the last one. If you hadn't seen the room or the place that you were stringing it through, how would you put the pinches in?
Great question. So the example I showed where it goes through and it turns the valve, we had all the measurements, we saw the room, we knew exactly where to pinch it in advance. But in many unstructured scenarios, like disaster scenario, we wouldn't know. So there's two ways to do that. One is to put a lot of pinches, pre-pinch it in a bunch of places that you might need, and then whenever you don't want to turn, we have a way of pressurizing the robot to peel open the pinch so the pinch doesn't actually stay on the surface. But the other way is through adding these little pneumatic lines around the outside, and that's reversible. You could actually go forward, look left, look right. The disadvantage there is that it's bulkier. There's a lot more material that has to get fed through the robot, and that will probably limit us in terms of how far we can go and how much we can curve. But you're absolutely right that unless we know the environment exactly in advance, we will not be able to pre-pinch everything just right. And it would be beautiful if we had all that information, but we don't in most applications. All right.
One last question of you. You must be developing a lot of patents in all of this research, and those are property of the university, or?
Yes. Yeah, that's right. The patents, things that are invented at the university are owned by the university. In some cases, we also collaborate with companies, and then they're co-owned by both. And that actually can be an advantage because then inherently there's a company interested in licensing and participating in the development of the technology into a product.
Helping to fund research.
That's right. All right. Thank you all very much.
I know you all know this as alums, but these talks today are just, to me, a reminder of just what an amazing, amazing place it is here at Stanford. I am very pleased to introduce Debbie Senesky. Debbie is an assistant professor of aeronautics and astronautics, and by courtesy, electrical engineering. Her research is centered on the development of micro and nano systems for operation within extremely harsh environments, and she will explain to you just how harsh those environments are. She holds a PhD from UC Berkeley, and this afternoon she will talk about nanoscale electronics for space exploration. So please join me in welcoming.
Okay, thank you so much for the introduction, and thank you all for coming here today. Again, my name is Debbie Senesky. I'm an assistant professor in the Aeronautics and Astronautics department. I'm going to talk a little bit about my research, but before I do that, I'm going to tell you why it's an exciting time to be an aerospace engineer. But we have to go back 100 years to really grasp and understand where we are today with aerospace engineering. So this is an image of the experiments of the Wright brothers in the early 1900s, so over 100 years ago. They conducted various failed experiments in order to achieve human flight, in order to allow us to traverse the sky. They were able to use and compile mechanical structures as well as propulsion systems to allow us to fly in a controllable and sustainable fashion. 70 years later, this work really inspired us to eventually do the same thing with rockets and place a man on the moon. So today, Elon Musk and Gwendolyn Shotwell are working together with their engineers at SpaceX to try to get to Mars. So Gwendolyn Shotwell was here on Wednesday talking about their work with the Falcon 9 rocket and also their experience with many, many failed rocket landings. So this image on the left-hand side here is showing their experimentation that didn't work out. But what was mentioned in Gwendolyn's talk is that it actually hit the target. Although millions of dollars, unfortunately, were lost in this experiment, they were able to launch and hit the target. Moving forward, years later, now the Falcon 9 rocket can actually land on the target. How many of you have seen this video recently? If you have not seen this video, please watch it. It really is quite inspiring. And so the goal here is to be able to reuse rockets so that we can eventually go to Mars and maybe even come back. Or perhaps we have space tourism as well, right, where we would travel around the moon. And so this is the spirit of aerospace engineering right now, really doing the impossible. Many of the students, undergraduate students and graduate students here are really interested in this area, and our department recently started an undergraduate program 2 years ago. So we haven't officially graduated any aerospace undergraduates here at Stanford, but stay tuned. In a couple of years, we will have graduates in our program. So why space exploration? So we're really interested in understanding our solar system. We want to know big questions. Are we alone? Is there another planet that we could live on and have a new type of habitat? Are there resources that we can harness and bring to Earth for our benefit and for our sustainability? But in order to do all of those types of exploration, we need to conduct experiments and missions on various types of terrains, very extreme environments that are radiation rich. They also have extreme temperature cycles from very, very cold cryogenic temperatures all the way to extremely hot temperatures. Also, our various planets and bodies in our solar systems have different terrain that we have to navigate. So my research is focused on developing technology for extreme harsh environments. Our current focus in particular is in the Venus environment. So Venus is our neighboring planet. There's an image on the left-hand side of Venus. And Venus is actually very much like Earth. It actually has the same mass and the same diameter. So it's very much like Earth with respect to its density. But it's also very, very different from Earth. Number one, it doesn't have a magnetic field. Number two, it doesn't have a moon. Also, it doesn't have tectonic plates like Earth. More importantly, it also has an extremely harsh environment. The surface temperature of Venus is around 480 degrees Celsius. Also, it's chemically corrosive. It has supercritical CO2 in its ambient, as well as sulfuric rain clouds. So this is an image from the first color image of the Venus surface, taken in 1982 by the Soviets. Again, many failed missions were conducted before this. The US has yet to send a lander to Venus. However, there are many proposed missions and various design concepts to do that in the near future. So what are some of the challenges with exploring a place like Venus, our neighboring planet? So what would happen if you were to put your cell phone on the Venus climate? If you were to land on Venus, what would happen to your cell phone? It would melt. It would bake. Anybody have issues putting your cell phone on your dashboard of your car in the sun? Right? So heat actually can degrade electronics. What happens is your semiconductor material starts to generate a lot of electrons due to the thermal energy, and your electronics don't work the same anymore. They work in a very unreliable fashion. So this is a chart of various semiconductor materials that can help us extend the operation points beyond silicon. Okay, so silicon, we're in Silicon Valley. It's a wonderful material. NASA and other aerospace researchers do use silicon. However, they have to actively cool it and shield it from the space environment. And that adds to payload. And every pound that you put in space costs $10,000. So until we actively have these reusable rockets, we really need to think about very carefully what we put in space. And every gram of material really has to function. And so there are alternative materials that my group has been working on, in particular, wide bandgap semiconductor materials. You could think of them as ceramic materials. So many of you may know ceramic materials that are reinforced, that are used to reinforce metals, such as diamond, for example. Diamond is a very hard material. But a lot of the challenges with many semiconductor materials is that they don't transport electrons, right? They're great thermally and mechanically, but it's very difficult to make something like a transistor or a sensor device out of these materials. So my group has been working with gallium nitride in particular. What's attractive about gallium nitride is that it has a very high melting point, 2,500 degrees Celsius. So thermally, it's very, very stable. It takes a lot of energy to break apart the gallium and nitrogen bond. In addition, it has a very high energy band gap. It takes a lot of energy for electrons to jump the valence band, thermal electrons. And so therefore, it can work up to 1,000 degrees C before thermal runaway starts to dictate the electron transport in your electronics. Also, due to the band gap, it's actually sensitive to the ultraviolet regime, which is very advantageous in optical imaging in space. So gallium nitride is an emerging semiconductor material. It is heavily used in the power electronics area because it can handle very high voltages and also function at very, very high frequencies. In addition, this material has been used to develop the blue LED, so Nobel Prize winning work for gallium nitride to create the blue LED. Other disciplines include sensing, solar cells. The highest efficiency solar cell actually has a layer of gallium nitride within it because it can capture a portion of the ultraviolet spectrum. In addition, micromechanical structures such as RF resonators and also nanostructures are being developed in this platform. So gallium nitride is a little bit different in comparison to silicon. So I just want to take some time to explain its transduction. So with silicon, in order to make a transistor, you have to dope the material. You bombard the material with either boron or phosphorus in order to make it more conductive. Gallium nitride is a little bit different because it leverages a quantum effect. So this is an image of the atomic arrangement of gallium nitride. If you start to sandwich composite variants of gallium nitride together, in particular aluminum gallium nitride and gallium nitride, what happens is you actually form a nanodimensional sheet of electrons, and it's called the two-dimensional electron gas. And so this is how the electrons flow through the material. It's through the generation of this composite material that forms a quantum well, a high density of electrons. The sheet of electrons, you can think of it as just a 1D sheet of electrons flowing through this composite material, and then we can modulate it through the implementation of a source, gate, or drain, just as you would with your silicon-based transistor. So it's a slightly different technology. So we have adapted the gallium nitride platform to create high-temperature electronics. So this is a cross-section of the electronic structure. We use silicon wafers. We do a lot of work to develop the buffer structure to be able to grow the device layer gallium nitride films. We also have shown that atomic layer deposited dielectrics actually help them work better at elevated temperatures. So unfortunately, it's a little bit hard to see, but this is a picture of a a glowing chuck at 600 degrees Celsius, and we have our gallium nitride chip on top of the chuck, and we're probing it, and we're actually able to get electronic signals. So these are IV characteristics going from room temperature all the way to 600 degrees Celsius. So this is a transistor with controllable electrons flowing through that two-dimensional electron gas at 600 degrees C. So this tells us that we can actually make high-temperature electronics for places like Venus. And we're also able to suppress a lot of the leakage in these types of devices through the introduction of nanomaterials. So my group is working to adapt this new semiconductor material platform to create multifunctional gallium nitride nanoelectronics. So in addition to a transistor, you can also think about designing sensor technology, resonator technology, energy harvesters, all on the same chip. So we can use the same material to create a multitude of devices. So these devices can then sense the external environment, they can also power themselves, and they can also communicate data. You could think of this as something like a Chipsat, right? You have multifunctional behavior of your electronic elements, however, they are fabricated all together on the same chip. So this is an example of a device that my student has developed. This is a gallium nitride pressure sensor. You can see here this chip on the right-hand side is 1 centimeter by 1 centimeter in size, and it actually houses about 40 prototypes of her sensors. So these are very, very small devices that can really do many, many things. What we do in order to test these devices is we use a small pressure chamber that can apply high pressures and temperatures at the same time, and then we're able to characterize the electronic signals of this type of device. So these are some of her results showing room temperature all the way to 300 degrees C. Again, you have IV characteristics. You have this resistance response and then saturation. So what that means is it's functioning like a transistor. It's able to switch. In addition, you have pressure sensitivity. So the device I've shown you here is an adapted device that actually you remove the substrate and you have a pressure-sensitive diaphragm. So as you apply pressure, it actually displaces the diaphragm and allows strain to be induced in your transistors. And as you increase the pressure, you get a shift in the IV response. And so you can use this to convert pressure signals to electrical signals that you can then process using your onboard electronics. So we've been collaborating with NASA to study these materials in harsh environments. In particular, we've been using the Venus chamber at NASA Glenn Research Center. This is a chamber that simulates the Venus conditions. It has all of the chemistry that you would find on Venus. Also, it has the pressure, 90 bar of pressure, and elevated temperature, 480 degrees Celsius. So I don't want to have this type of instrumentation in my lab. So I'm glad that NASA has this type of facility. So my students go to NASA every summer, and these are samples here of various ceramic semiconductor materials that we've inserted into the Venus chamber. And we're studying the weathering of these materials to really understand the evolution of the material due to the caustic Venus environment. In addition, we've been working with a startup company to look at nanocoatings that might help with its weather resistance. So as I mentioned before, Venus has a sulfuric ambient. It actually has sulfuric rain. So that can really degrade electronics. So what if we had a nano coating that actually repelled that sulfuric rain and prevented it from actually etching and eroding the surface? So what you're seeing here is a droplet of sulfuric acid. Yes, my students have a lot of fun in the lab, and we worked very carefully with the various chemistries that we utilized. This is the nanocoating, and you can see this sulfuric acid is balling up on the surface. It's not wetting the surface, it's actually repelling the surface. And so that can help with allowing electronics and other materials that would be used in a Venus lander to actually resist the sulfuric rain found on Venus. So this is a new area that we're looking at, and we are actively pursuing a deeper understanding of how these materials actually repel the Venus environment. So another mission that is emerging in the field of aerospace is being able to go to deep space using Chipsets. So actually exploring beyond our own solar system. And so in order to do that, it would be very, very difficult to conduct with your traditional spacecraft. You would need a lot of energy and propulsion to get to somewhere like Alpha Centauri, which is our nearest solar system. So what is proposed is that you have a variety of chipsets that would be able to sense, communicate, and power themselves beyond our solar system. And so these constellation of chipsets would then communicate with each other, collect information, and send it back to Earth. But how do we get there? So one of the concepts is to use laser-based propulsion on Earth to launch chipsets that are propelled with a light sail. So you can use radiation pressure on a very thin membrane in order to propel these chipsets over to Alpha Centauri. So this is called the Starshot Breakthrough Initiative. It's being funded by Stephen Hawking and Yuri Milner, and they are looking to really send a chipset to Alpha Centauri. It would take 20 years to get there, and would be really interesting to understand more information outside of our solar system. But in order to develop these chipsets, you need to have technology that would be resilient over that entire journey. Again, there's going to be thermal cycling and also radiation attack. So depending on where you are in the space environment, whether in low Earth orbit, Venus, or deep space, there's going to be a variety of temperature swings and also a variety of radiation levels. And this is just shown here graphically. And so radiation is composed of energy, high energetic particles such as protons, electrons, or neutrons. And when they bombard your materials, they actually degrade your materials. And when they bombard electronics, it could actually degrade your signal. And so what we do now is heavily shield the electronics in order to allow them to perform in these radiation-rich environments. So my group has been developing another platform for high temperature and radiation-rich environments. We've been using graphene, which is a sheet of carbon atoms. It's an atomic layer thick sheet. So you can think of the carbons in a chicken wire formation. It actually has amazing mechanical properties. It's stronger than steel. Also, it has interesting electronic properties as well. It is a transparent material, and so it allows all of the optical spectrum to be transmitted. And so we've been using this as a conductive layer to develop ultraviolet photodetectors. So what we do is we transfer the graphene to our gallium nitride substrate. We do patterning, and then we create these interdigitated electrodes, which are conductive. And when we shine ultraviolet light onto this structure, what happens is we generate a current. And that current is proportional to the intensity of the ultraviolet light. And so we can use this as an ultraviolet detector. This is an image of our graphene on gallium nitride device. So the black fingers there are around 10 microns in width. You wouldn't be able to see this graphene with your own eye. We actually have to use a scanning electron microscope in order to resolve the graphene and actually know that it was printed there on the substrate. So we have tested this device under ultraviolet conditions, and also we've irradiated it with protons at various fluences. So the black curve is the IV response under dark conditions, and then the colored curves are the IV response or current voltage response under ultraviolet stimulation. And we observe the evolution of the IV characteristics upon irradiation of protons. And we can see that those IV curves start to collapse. So the radiation is actually not degrading our device, and this is an unshielded electronic device that's surviving high proton irradiation. So we've studied the responsivity of our device over increasing fluence, so over protons per area. We can see as that increases up to around 2.5, 10 to the 13 protons per centimeter square. It's very, very stable in comparison to your traditional metal electrodes. We've also studied the response of the graphene layer using Raman spectroscopy. Raman spectroscopy is a materials characterization technique. It actually allows us to get the fingerprint of the material. We can identify the type of material and also the crystallinity of the material. So what you're seeing here is the graphene before the proton irradiation and after proton irradiation. And you can see we're getting sharp peaks. So this 2D peak is a very high intensity peak, and that tells us that the graphene is of very good quality. And after radiation, we see minimal degradation in that peak. And so that's telling us that even after an intense irradiation, this nanomaterial is able to survive. So we've adapted this sensor to create instrumentation for a CubeSat. So we have our individual ultraviolet photodetectors. We've placed them in an array, and we've also placed an optical aperture on top of that array. So as the sun is shining on this sensor, it's illuminating one of these sensors, and we can monitor the intensity and then back calculate the location of the sun. So we've implemented this miniature sun sensor on a CubeSat through the QB50 program. It's a constellation of 50 CubeSats at various universities around the world, and Stanford has a CubeSat, the Discovery CubeSat. And so you can see an image of it here, the solar panels, and our gallium nitride graphene sun sensor, optical sensor. And so we're waiting for this CubeSat to be launched so we can evaluate and validate the performance of our sensor. Finally, we're implementing our sensors on a suborbital launch as well. And this is a great training opportunity for students because they get to engineer under time constraints. They also get to engineer under size constraints and power constraints. They really have to be innovative in order to implement their devices on things like CubeSats because, again, there's a lot of space constraints in particular. So this is an image of our sensor payload. We have some interface electronics. We also have our gallium nitride sensor, and we're gearing up to implement it on the Wayfinder CubeSat, which is developed by Boreal Space, which is a company based out of NASA Ames. We're also working with interorbital systems to launch this CubeSat in suborbital flight, and we're going to measure the magnetic field signatures of the Earth during that suborbital flight. So hopefully I've given you a sense of the development of electronics for harsh environments. So in addition to space exploration, there are also ground-based applications where this work can benefit, such as oil and gas exploration, monitoring of combustion engines, and also geothermal well bores as well, which also have extremely high temperatures, and it's very, very difficult for electronics to perform and survive. So with that, I'd like to acknowledge the students in my group who have conducted a lot of this work and also the funding sources as well. And I'm happy to take any questions.
So do you know what proton radiation is doing to graphene? You know, why is it changing the IV?
So it actually is quite resilient. It's not doing much to graphene, but there are vacancies. If we analyze the peaks in our Raman spectroscopy, there are some vacancies in the lattice. I'm sorry? It looks like it's becoming more conducting. Why do you say that? Yeah. Oh, okay. Yeah, so what could be happening is that when you irradiate materials, you can actually compress the atoms, and so that could be changing the electrical properties as well. Radiation can physically, compress and bombard the material as well.
Well, on the topic of geothermal, I live in Hawaii. And in the late 80s, the volcano on the Big Island started erupting again. Mm-hmm. And it didn't used to be a problem because the trade winds would blow those winds to the south. And the fumes, of course, are very high in sulfuric acid. Mm-hmm. And now with climate change, we have week after week of no trade winds. And those fumes come creeping up the Hawaiian chain. Mm-hmm. Now, obviously, your work isn't going to do anything for us humans. But can you think of any applications for, because even the plants suffer when we've got bad fog. Yeah. So it must apply to machinery and things like that are on Earth atmosphere, but.
Yeah, certainly. We've worked with the University of Hawaii to monitor volcanic-like activity. So it's interesting what's happening in the lava. It's really difficult to understand the profiles of the lava. So this sensor technology could be adapted to monitor volcanic signatures and volcanic behavior in real time. And you were talking about the sulfuric, so monitoring that from a chemical point of view. There's nothing we can do to stop it, right? But we could monitor. And so using some of this instrumentation would allow us to go, again, beyond silicon to a higher temperature where today's instrumentation can survive.